Welcome to Free Learning Academy. Let's simplify process synchronization. Imagine two people trying to write in the same notebook at the exact same time. One writes a number, the other erases part of it, and suddenly the final answer becomes meaningless. Now replace those two people with programs running inside a computer, and that is where a major operating system challenge begins. This challenge is called process synchronization. It may sound technical, but the idea is very practical. Whenever multiple processes or threads work together and share data or resources, they need rules and coordination. Without that coordination, the system can become incorrect, unstable, or inefficient. In this part of operating systems module, we begin understanding how the OS keeps order when many activities happen together. To understand why synchronization is needed, first remember that modern computers rarely run just one task. Even when you think your system is idle, many background activities are active. A browser may be downloading updates, the antivirus may be scanning files, music may be playing, and system services may be running silently. Earlier, when we discussed processes and threads, we learned that the CPU rapidly switches between tasks to create the effect of parallel work. In multi-core systems, several tasks may truly run at the same time. This improves speed and responsiveness, but it also creates situations where multiple tasks try to access the same thing together. Let us take a simple banking example. Suppose your bank account balance is 10,000 rupees. At the same moment, one process handles an ATM withdrawal of 2,000, while another process handles an online purchase of 3,000. Both processes read the same original balance before updating it. If they work without synchronization, one may save 8,000 while the other saves 7,000. The correct balance should be 5,000, but the final stored result may become wrong. This happens not because the computer is slow, but because both operations interfere with each other. Synchronization exists to prevent such mistakes. Now think about something simpler, like printing documents in an office. 10 users send print commands to one printer. If the operating system allowed all processes to directly control the printer at once, pages could mix together. Half of one report may print, then a page from another report, then another interruption. The result would be chaos. Instead, the OS coordinates access to the printer. One job gets control, others wait in line, and each finishes properly. This waiting and controlled access is another everyday example of synchronization in action. One important idea here is shared resources. A shared resource is anything multiple processes may need at the same time. It could be a file, printer, memory area, database record, keyboard input, or network connection. Since these resources are limited, they cannot always serve everyone simultaneously. If two programs try to modify the same file together, data may get corrupted. If multiple threads update the same counter in memory without coordination, values may be lost. So, synchronization is really about fair, safe, and correct sharing of resources. Another important reason synchronization is needed is data consistency. Imagine an online shopping site showing product stock. Only one item remains. Two customers click buy now almost together. If both requests read stock as one and proceed independently, the system may sell the same item twice. Customers get disappointed, refunds happen, and trust is lost. Proper synchronization ensures that once one process starts updating stock, another must wait until the update is complete. Then the second process sees the latest value. This keeps information accurate and reliable. Synchronization is also essential for process cooperation. Not all processes compete. Many need to work together in sequence. Imagine a video streaming platform. One process downloads video data, another decodes it, and another sends it to the screen. If the display process runs before data is ready, nothing useful happens. If the downloader keeps sending data faster than others can handle, memory may overflow. So processes often need timing coordination, not just protection. One process may need to wait until another finishes a step. Synchronization helps organize such teamwork. You can think of synchronization like traffic signals at a busy intersection. Cars are processes, the road is a shared resource, and signals decide who moves and who waits. Without signals, Everyone may rush forward and collide. With proper control, traffic flows smoothly. In the same way, synchronization does not exist to slow the system down. It exists to avoid collisions, confusion, and waste. Sometimes a short wait now prevents a much bigger failure later. There is also a security and stability angle. If processes freely interfere with one another, a buggy or malicious program could damage shared system data. One process could overwrite memory being used by another. Important files could become corrupted. System services might crash. The operating system uses synchronization along with memory protection and access control to maintain order. So, this topic connects closely with earlier discussions on process management, system calls, and user mode versus kernel mode. The OS is not just running tasks, it is governing their interactions. Of course, synchronization itself must be designed carefully. If processes wait forever, the system can freeze. If one process never gets access, starvation may occur. If two processes keep holding resources while waiting for each other, deadlock can happen. These are advanced issues we will study later in this module and the deadlocks module. For now, the key understanding is that synchronization solves one set of problems but must be implemented intelligently. So, in simple terms, process synchronization is needed because modern systems run many tasks together, and those tasks often share data or depend on each other. Without synchronization, balances become wrong, files become corrupted, printers become chaotic, stock counts become inaccurate, and cooperative tasks break down. With synchronization, tasks work in the correct order, resources are shared safely, and results remain consistent. It is one of the hidden reasons computers feel reliable even while doing many things at once. In the next parts, we will explore the exact problems that occur without synchronization, starting with race conditions and the critical section problem. That is it for this video. See you in the next one.